All right, welcome to day 2 of Unit 10, Trigonometry. We're just going to do more practice solving using sine, cosine, and a little bit of tangent. So I'm adding that to our cover sheet right there. So let's scroll to day 2 in our notes. All right, starting with our first question, if sine of x equals 4 over 5, what is tangent and cos of x? Now, we talked in day 1 about how right triangle trigonometry is with right triangles. So what I'd like you guys to do is draw a right triangle right in this space. And let's just call one of the angles x, because that's what it's saying, sine of x. Now, when I tell you a sine, I'm telling you an opposite over a hypotenuse because of what we know about SOHCAHTOA. Those are our ratios. So that means from our angle, the opposite side must be 4. The hypotenuse, which is opposite the 90-degree angle, it's our largest side, must be 5. So I need to figure out the adjacent side if I want to talk about tangent and cos, because tangent is opposite over adjacent, according to SOHCAHTOA, and cosine's adjacent over hypotenuse. Now, as a reminder, adjacent means the side next to our angle, but not the hypotenuse. So that would be this side right here. Now, I'm not going to call my missing side x because I've already used x in my diagram. That's really important for you all to make sure you pay attention to. So let's pick literally any other letter. Maybe I call this A. Okay? Now, if I have two sides of a right triangle and I want the third, we're using our Pythagorean theorem. That is not a new thing for us to be doing. So I can do a squared plus 4 squared equals 5 squared, because c is always the hypotenuse. So a squared plus 16 equals 25. I'm solving getting a equal to 3. Okay. Now, like we said, if I want tangent of the angle, that's going to be opposite over adjacent. So our opposite side is 4, and our adjacent side, which we just found, is 3. So tangent of x must be 4/3. If I want cosine of x, that's an adjacent over hypotenuse, so that would be 3/5. All right, and that's question 1. All right, question 2, a little bit more of a word problem. The Occupational Safety and Health Administration, OSHA, provides standards for safety at the workplace. A ladder is leaned against a vertical wall according to OSHA standards and forms an angle of approximately 75 degrees with the floor. If the ladder is 25 feet long, what is the distance from the base of the ladder to the base of the wall and round to the nearest hundredth? Okay, so let's draw a picture here. We're going to draw a right triangle, because all of these are going to involve the right triangle in order to do trigonometry. You want to add some rungs. There's your ladder. Now, if we reread this, it says it's leaned against a vertical wall and forms an angle of approximately 75 degrees with the floor. So I want you guys to put a 75-degree angle right in that spot. The ladder is 25 feet long, so I can put a 25 on what will be the hypotenuse. I want to know what the distance from the base of the ladder, so that would be right here, to the base of the wall is. All right, so there's your right triangle with our sides labeled. You'll notice I have an adjacent side and a hypotenuse. So if you think of SOHCA, that means we're going to be doing cosine. So this is cos of 75 equals x over 25. And now we're set up like we were yesterday. So if I put this over 1, I can cross multiply. And this would be 25 times the cosine of 75. Now I go to my calculator. And you can type it in just as you see it. So to the nearest hundredth, I am getting 6.47. How high on the wall does the ladder make contact? Round to the nearest hundredth. Now, technically, I could use my unrounded answer and do Pythagorean theorem, but let's use some trig again. This is 75, this is 25. They want now this vertical distance. Now that's an opposite over hypotenuse, which changes my function. Now I'm looking at sine. So sine of 75 equals x over 25. So if I cross multiply, x is equal to 25 sine of 75, and then I go to my calculator. And to the nearest hundredth, I'm getting 24.15. And that's using cosine and sine to solve my triangle. All right, next question. A shipmate set a boat to sail exactly 27 degrees northeast from the dock after traveling, from the dock, period. After traveling 120 miles, the shipmate realized he had misunderstood the instructions from the captain. He was supposed to set sail going directly east. How many miles will they have to travel directly south before they are directly east of the dock? And round your answer to the nearest mile. All right, so imagine this. You are captaining this boat, or your shipmate, whatever. You're going on this boat and you're going in the wrong direction. And then you get here after 120 miles and you're like, oh no, I went the wrong way. So then you backtrack in order to get back on path, okay? I need to figure out how much they had to travel south, which is this distance right here, going down to get back on the correct path to go directly east of the dock. So if we look at the 27-degree angle, that means I have an opposite and a hypotenuse because I have the side opposite the right angle. That means we should be using sine. So sine of 27 equals opposite over hypotenuse. And then we just cross multiply. So to the nearest mile, 54 miles. All right, using your answer from part A, how many extra miles did they travel by going the wrong direction compared to just going directly east? And round our answer to the nearest mile. Well, first of all, basically the long way is how I'll label this. Is they went 120 miles plus an additional 54, so they went 174 miles in this long direction. How is that compared to if they just went the right way the first time around? So let's call that y in my diagram. So if we use this 27-degree angle again, and then y and 120, now that's an adjacent over a hypotenuse. So the short way would be using cosine. Cosine of 27 equals adjacent over hypotenuse. All right, so let's find out that distance. So if I go to my calculator and type in 120 cosine of 27, it's like 106.92 ... I think I copied that right. Yep, 106.92. So they're asking how many extra miles did they travel? Well, if I do 174, take away that 106 number, they traveled 67 extra miles. I think that's what I said, right? Yeah, 67 extra miles. Yikes. That's quite the big mistake. All right, moving on to the next page. All right, now I'm going to skip question 4. If there's ever a time you guys want to revisit that, feel free to go for it. I'm going to jump on down to number 5. A polygon is inscribed in a circle if each vertex of the polygon is on the circle. So they're just defining the picture you're looking at. Inscribed means it's inside the circle, and each vertex is on the edge of the circle. A regular pentagon, meaning all sides are congruent, with side lengths of 14 centimeters is inscribed in a circle. What is the radius of the circle? And round to the nearest tenth. Okay, so each of these side lengths would be 14. Now, in order to do trigonometry, we have to have a right triangle. So right now I don't have a right triangle in here. I'm going to have to create one. Now, the radius of the circle would be from the outside edge to the center. So I'm going to label that R. Which means if I draw from H to C here, that would also be R. Those are two radii. Here's where I'm going to create the right triangle. I want you guys to draw a perpendicular line, an altitude of that triangle, just like so. Wow, that turned out super wiggly. Let me try again. All right, there we go. That's a little bit better. So there's your right triangle. Now, based on what we know from Unit 9, if we have an isosceles triangle, which is what this shape is, and we drop the altitude to the base, that means it's going to split the base in half. So that means that this 14 I can divide into 7 and 7. Now, we're also missing some information about angles. So, let's think about this for a second. If this is a pentagon, meaning 5 sides, there's technically 5 triangle slices here, okay? If you have 360 degrees in a circle and you divide that by 5, that gives you 72 degrees. So that means this little angle right in here is 72 degrees. But remember from Unit 9 how if we drop the altitude, not only does it split the base, it splits the angle at the top. So I'll zoom in here for a second. This 72 degree angle is actually 36 and 36 now. Okay, so make sure you all have your picture labeled exactly as that. Remember, our end goal is to find the radius. We're going to focus right here. Which I don't love that I just colored over that. Let me actually grab my highlighter. Right here. Let's focus on this triangle. There's your right triangle. I'm going to redraw it. Here's your right angle. This is 7. This is 36 degrees. And this is your radius. So something that started off super complicated now breaks down, based on what I know about isosceles triangles, now breaks down just to a right triangle trig problem. Based on the 36, you have an opposite and a hypotenuse. So which trig function makes sense? You should be thinking sine for SOHCAHTOA, so. So sine of 36 equals opposite over hypotenuse. And now we just need to solve that. So if I cross multiply, I would end up with 7 equals R times the sine of 36. So in order to solve for R, I'm going to divide by the sine of 36. Seven divided by the sine of 36. So to the nearest tenth, we're getting 11.9. All right, very good. All right, we're going to do a couple more of those questions. Ooh, that jumped a little bit. Okay, a couple more of those types of questions. So get comfortable with drawing in our diagrams here to create right triangles. All right, next page. Next and last page, I believe. Yeah, next and last page. A regular hexagon, so 6 sides with a radius of 9 centimeters, is inscribed in a circle. Use a trigonometric ratio to find the length of the side of the hexagon. Okay, so now we're basically just going in the other direction. So, if I draw in some pizza slices here, right, there are basically 6 pizza slices here in this circle with this hexagon, which means each angle is 60 degrees. They're telling me the radius is 9, so I'll just throw a couple 9s in there. Now, I ultimately want to find the side of the hexagon, so that's that entire distance right there. I have to get a right triangle in here somehow. So like the last example, let's draw in the altitude, which splits this angle into 30 and 30. Let's call this little side in here x, which makes this little side right here x, which makes DC, which is one length of the side of a hexagon, 2x. Now again, if this is a little bit complex, pick one of the triangles. There it is. And just redraw it. So based on what's given, I have opposite and hypotenuse, which means we're going to use sine. Cross multiply. And then go to my calculator. I end up with 4.5. Now at the end of the day, I wanted the entire length of the hexagon, so keep in mind we're going to do 2x, which means 2 times 4.5. So that means the side length is 9. Okay, now let's talk about this question for a second. There's a reason why I said use a trig ratio to find the length of the side of the hexagon. That's me forcing your hand to make you use trigonometry by using the sine of 30 equals x over 9. There's technically two other things you could do here. If you think about what we know from Unit 9, we know that this is technically a 30, 60, 90 right triangle. And they're ultimately looking for the shortest side here. The relationship between the shortest side and the hypotenuse is double, so going backwards would be half. What is 9 divided by 2? 4.5. So you could really use 30, 60, 90 triangle relationships to solve this. And notice how I'd end up with the same answer. Now another thing to consider is if this is a hexagon, there are 6 sides, which makes each angle 60 degrees. We know all these radii would be congruent, right? Wouldn't that mean these angles have to be congruent? And we know there's 180 degrees in a triangle, so 180 minus 60 is 120. Divided by 2 is also 60. So technically, and this is specific to a hexagon, we actually have equilateral triangles. So when I gave you the radius of 9, I ultimately was giving you the side length. So fun facts there. There were other ways to solve this, which is why I had to say use a trig ratio to solve. All right, let's go on to example 6. Sorry, my thing's jumping all over the place. Okay. Now, every time you and I have been dropping the altitude, is what I keep calling it in these polygons, you're actually drawing in what's called an apothem. So a segment drawn from the center of a circle perpendicular to the side inscribed in the polygon is called the apothem. So see, now it looks like the altitude of an isosceles triangle, just like so. I want to find the length of the apothem to the nearest tenth of a regular pentagon inscribed in a circle whose radius is 10. So that's this visual right up here. Okay, so the radius is 10. Now, again, if this is a pentagon, there's technically 5 pizza slices here, which makes each angle 72 degrees, because 360 divided by 5 is 72. Now, as we did previously, that means that each of these little angles in here is 36, because it divides, or this altitude would divide this angle in half. I want to find the apothem. Here's the right triangle you can focus on. And again, if that's confusing, redraw it. Maybe better than what I did, but redraw it. Here's your right angle, here's the 36 degree angle, here's the 10, here's the x. So based on what I have given here, I have a hypotenuse and I have an adjacent side. Therefore, I should be using cosine to set up and solve for my apothem. Okay, so that means I'm using cosine of 36 equals adjacent over hypotenuse. And then I just cross multiply and solve. So nearest 10th, 8.1. All right, final question, getting out of the hexagon, pentagon world. Now I have similar triangles. So bringing it back to Unit 8. Given the similar triangles below, if cos of A is 5 over 12, what's the value of x? All right, I love these types of questions. They're really tying in a lot of information here. So let's write this out for a second. Cosine of A equals 5 over 12. Here's your little angle A that they're referring to. Now, when they're telling you cos of A is 5 over 12, they're ultimately giving you an adjacent over a hypotenuse because that's how SOHCAHTOA works. So from this angle A, my adjacent side would be right here. That means we're going to label that 5. The hypotenuse, which is opposite the 90-degree angle, is going to be 12. Now, notice how I did like little squiggles on the hypotenuse. Let's actually do the same thing in my other similar triangle. So I know the 12 and the 14.4 are going to correspond. Now, I need to solve for x. Now, if you pay attention to how our correspondence here works between the 90-degree angle and the single arc that they gave me, those sides would correspond, which have no information on them, which then means this 5 must be corresponding to this x. So now that I've color-coded this, you should be able to set up a proportion and solve. Blue is to blue, so x is to 5, as red is to red, so 14.4 is to 12. So blue is to blue, as swiggle is to swiggle. So if I cross multiply, I'm going to get 12x equals 5 times 14.4. So 72. So if I take 72 and divide by 12, x equals 6 is my final answer. All right, so I'll tell you right now, on the final exam, you love asking questions like this because it ties in more concepts than just SOHCAHTOA. They're tying in your similar triangles. So if you mess up your proportion, even though you identified the cosine correctly, you could get the wrong answer. So really good question. All right, so that concludes our notes for day 2 of more problems with sine, cosine, and a smidge of tangent in there from right in the beginning.